Hey guys, and welcome back to my channel. And this week I'll be talking about stretches, horizontal and vertical, and I'll be looking at how they are algebraically and graphically represented. So let's start off with the two types of stretches. First of all, we have a vertical stretch, which is represented by y equals a factor times f of x, but we also have horizontal stretches, where y is equal to f and the factor is multiplying the x inside the brackets, and soon we will see what the difference between the two is. So let's start off with a vertical stretch. So a vertical stretch is when we have a factor outside of our original function, f of x. And we say, when we refer to this, we say by a vertical stretch factor of a. So for example, if our vertical stretch factor is 3, then we will have 3 times f of x. If our vertical stretch factor is a half, then we will have 1/2 times f of x. Now, what might this look like, and what generalizations can we make? So let's do a concrete example first to get a feeling. Let's say we have x squared, and I graphed this using Desmos. What do you think will happen if we have 3 times x squared, or if we have 0.3 times x squared? So have a little think about it, and then I'll reveal the answer to you. So let's start off with the 3x squared. This right here is a vertical stretch factor of 3. So if you look at the original graph, it's as if taking every single point and multiplying it by 3. Everything goes up. So for example, here at 4, we're going to have 12, which is going to be way up there. So for every single output that we get, we then multiply it by this factor of a. So our graph will end up looking narrower. So if we look at the graph that we have drawn, or that we have gotten, we will get this. And this is referred to as an extension. And why is it an extension? Because it feels as if we're taking the original graph, the red graph, and we're pulling it up to get this more narrower graph. Now let's think what would happen if it was 0.3 times x squared. Well, in that case, every single one of our points would get multiplied by 0.3. And this would, in this case, actually compress our graph, because it would make it wider, because for every single point we would divide it, or we would have a factor less than 1. So what this would look like then, if our vertical stretch factor was 0.3, is like this, exactly like we talked about. Each point is going to get multiplied by 0.3, which will give us this new graph right here. And this is called a compression, because it's as if we're compressing the function from down so that it becomes wider. So what generalized statements we can make from this observation right here is that if our absolute value of a, is greater than 1, then we have an extension, because we're multiplying something by a factor greater than 1, so the value is going to be greater than the original value, and we're pulling everything up like we did right here. Now, if the absolute value of a is less than 1, then we have a compression, because for every single value we're multiplying it by a factor that's making the new value be less than the original value, so we're pushing everything down. And if a is equal to -1, well, that's just a special case of this vertical stretch, and it's going to be a reflection in the x-axis. And to show you what I mean, I have made another little Desmos graph right here, where for every single y, we get the same y value, but it's in the negatives. Keep in mind that all of these factors still work when your a is negative, when your function is negative. That's why we have an absolute value. For example, if we take negative x squared right here, and we have negative 3x, then our new function will look something like this. Obviously, this is very bad drawing, but you get the idea. And the way that we approach vertical stretch factors is that at every x value, we have a y value, which then get multiplied by said factor. And this is what makes it be stretched vertically. So we're either stretching it vertically up or vertically, more to say down, but it's either opening, becoming more narrow, or becoming wider. Now let's look at the horizontal stretches. And here the language gets a bit tricky. So when talking about horizontal stretches, if we say that there's a horizontal stretch with a factor of a, actually what we're going to see in the brackets is 1 over a. Or if we say that a horizontal stretch factor is 1 over a, then inside the brackets we'll have a. And let me show you what I mean. If we have a horizontal stretch factor of 1/3, then we're going to have f of 3x. If we have a horizontal stretch factor of 3, we're going to have f times 1/3 x. So keep this in mind when talking about horizontal stretches, because it might lead to some miscommunication, and also the generalizations that we make. I will be referring to a as the word that we speak, horizontal stretch factor of a, implying that whatever is in here is 1 over a. So let's look at the same example, but now a horizontal stretch factor. So if we have a horizontal stretch factor of 2, we're going to have 1/2 of x squared. And think about what this might look like, and then come back and see. Well, in this case, because our stretch factor is greater than 1, but actually we're multiplying x by 1/2, we're going to have a wider graph. We're going to have a compressed graph, because for every single x, at x equals 1, we're actually calculating x is 1/2. So we'll get the point right here at 1. Now, at x equals 2, we're actually calculating x of 1. So we have this value. And we continue doing this to get this new graph, which is way more wider and is compressed. Now think what would happen if our horizontal stretch factor was less than 1. So for example, 1 over 3. Well, this is the opposite of what we just looked at. Basically, for every single x, at x equals 1, we're actually calculating what x is at 3. So if we see x at 3, that is exactly what we now get at x equals 1. So now we are making our graph narrower, which is an extension. And you might already be seeing the difference between a horizontal and vertical stretch factor, even though they do look quite similar. Here, we're taking our original point and we're moving it horizontally, right? Hence the horizontal stretch factor. But here, we were taking our original point and we were moving it up. That was the logic behind it, which is vertically up. So let's generalize the statements that we have just made here. So if our absolute value of a is greater than 1, and again, I am talking about when we have a horizontal stretch factor of a, which leads to f of 1 over ax. Because if your horizontal stretch factor is 1 over a, and this is already accounted for, then these statements will be reversed. But I'm talking about when your horizontal stretch factor is a, and then your function is going to end up being 1 over a times x. So if the absolute value of a is greater than 1, then you're going to have a compression, because you'll be multiplying every single x by something that is less than 1, because of the 1 over a in the actual graph. Now, if your absolute value of a is less than 1, then you will have an extension, because you will be multiplying every single x value by something that is greater than 1. And actually, now that I think about it, a better way to show this is a compression. Because this is a horizontal stretch factor, a compression will be going in and an extension will be going out like this. So you, again, see the difference between the two. And lastly, if a is equal to -1, then you're going to have a reflection not into the x-axis like last time, but into the y-axis. And let me show you what I mean. So unfortunately, x squared would not look much different, but this function right here, you can see what I'm talking about. At every single x value, we're going to take it and we're going to multiply it negative. So at 1, we're not taking f of 1, we're taking f of negative 1. So we're going to have it right here. Oppositely, at negative 1, we're taking the value of 1. So we're going to have this point right here. So we're flipping not up and down, but left and right. And that is the main difference. That at every single y value, we are actually taking the negative x value of our original graph. So I hope you wrapped your head around both of these stretches. Stretches are one of the most fundamental types of transformations, and I hope you understand. I hope you refer back to these little generalizations that we made. I hope you learned something new, and I hope you have a good feeling about how you can use this. And see you next time.